Bismillah ar-Rahman ar-Rahim. Now, after we discussed the meaning of power series and the convergence of power series, we need to see an application for this. And the application will be like this: how to represent a function by a power series. So the title is Representations of Functions by Power Series. If we are given a certain function, a given function, can we represent it by a power series? We will answer partially the question in this talk, and then we will have a systematic way to find the answer. So partially, in this talk, we will answer the question of representing a given function by power series. And all the discussion will be based in the very famous geometric series we have, that is 1 over 1 minus x is equal to 1 plus x squared plus etc. You remember we have the geometric series. We said if we have a geometric series that is a series of the form, let's say n equal to 1 up to infinity a times r to the power n minus 1, that is a series of the form a plus ar plus etc., where we have the division of 2 in sequence terms will give us the same ratio called r. We said if this ratio, absolute value of that ratio is less than 1, then the series is convergent and it has the sum to be equal to a over 1 minus r. If we apply this formula, we have a geometric series whose ratio is x, because x over 1 is x, x squared over x is x, and etc. So the sum of the series will be just a, which is 1, over 1 minus r, which is equal to x. And we know that this makes sense only if the absolute value of the ratio is less than 1. We will use this specific identity, let's call it, or this specific representation of 1 over 1 minus x as a power series to express different type of functions that has a relationship with this in terms of power series. So today we will just express some functions, let us say, in terms of power series. Let us do that in the following exercise. So exercise says find the power series representation of a given function, let us say of the following function. So I start with part A. So this is part A that says 1 f of x is equal to 1 over 1 plus x squared. Okay, fine. How to express this one as a power series? Let us ask the question. Can we rewrite this in terms of 1 over 1 minus x as a sum of a geometric series? The answer is yes. If you look carefully for this function, you can rewrite it as 1 over, instead of 1 plus, I will write it as 1 minus what? Minus x squared. This is what we have. Exactly, this is what we have. I'm just rewriting it in the form we have 1 over 1 minus x. Okay, so using the same idea, what is the sum of this? The only thing we need to do is to go back to the series. We have n equal to 0 up to infinity. We come to this result here, and we will replace x by minus x squared. So that will give minus x squared all to the power n. Okay, we need to be careful here. When we move from the left-hand side to the right-hand side, we should be caring about the convergence. And the convergence here will be true if absolute value of x squared is less than 1. That is absolute value of r less than 1. Okay, simplifying, we have the following result that says 1 over 1 plus x squared can be represented as summation n equal to 0 up to infinity. This is minus 1 to the power n multiplied by x to the power 2n, and this is true only if absolute value of x again less than 1. Solving this inequality, absolute value of x all squared less than 1 will give what? Absolute value of x less than 1. So this is a representation of a rational function named by 1 over 1 plus x squared, and it happened to be equal to the sum of a power series. This is a power series. You can see now the coefficients, and this is just like x to the power 2n. So this is direct application for the geometric series formula we have here. Another one. Let's call this one part B, for example. We have a function, a rational function actually, which is given by it is 1 over x plus 2. Okay. The key here always is, can we rewrite it in such a form? 1 over 1 minus x or similar to this? And the answer is yes. By doing some algebra, of course, we can rewrite this one as 1 over 1 minus a ratio. So what do we have here? If you take 2 as a common factor, then this will be gained. 2 times, this is x over 2 plus 1. Okay? I will do one more step here. So I will rewrite it as 1 over 2. I will separate this times. Here I will write it as 1. I will switch these two. So I will have 1 minus x over 2. I'm rewriting the same thing here, but in different format. Now it is in the form we need. 1 minus u. 1 over 1 minus r, whatever you call it. Okay? So what is it equal to? Going back to the identity we have for geometric series, then this can be written as n equal to 0 up to infinity. Going back to the same formula we have here, I'm replacing only x by minus x over 2. So what I will get, I have minus x over 2 all to the power n. Okay. We need to be careful again about the convergence of the series. And we can write here, this series is convergent only if absolute value of x over 2 is less than 1. So absolute value of r less than 1 in other words. So let us simplify more. This will be equal to n equal to 0 up to infinity. That is minus 1 to the power n. This is x to the power n divided by, of course here I have 2 to the power n, but I have also 1/2 here outside, so this will be 2 to the power n plus 1, and the radius of convergence in this case will be 2, because I have absolute value of x is less than 2. You can see now clearly that these are the coefficients of the power series. This is power series centered at 0, whose radius of convergence is equal to 2. Okay, more examples will be gained now. Okay. Let us say this is part C. I will modify this question a little bit. So part C says you have a function f of x which is given by, I choose this one, x cubed over x plus 2. Okay. Can we find the power series representation of this new function? Going back to the previous discussions we did, especially the second one, we can easily see a relationship between them. This is x cubed divided by x plus 2. If we need to start solving this, what I will do is just take x cubed out of the fraction. So this will be 1 over x plus 2. Okay? Looking for this function here, 1 over x plus 2, this is exactly what we had in part B. So I can represent this by a power series. Okay, I'm multiplying by x cubed. So what do we have? What is the final answer then? Then this can be written as x cubed. Now I have a representation of this from n equal to 0 up to infinity. By my discussion before here, I have it to be minus 1 to the power n. And that is x to the power n divided by what? 2 to the power n plus 1. And this is true only if absolute value of x is less than 2. We are sure that this is convergent if absolute value of x is less than 2. Okay, fine. What I need to do now, I will take this one inside because this is running over n. It has nothing to do with x. So I can multiply by x cubed inside to get the following. N equal to 0 up to infinity. That is minus 1 to the power n, x to the power. Okay, here we have n plus 3, all divided by 2 to the power n plus 1. And it's very important to write here absolute value of x less than 2, because this is always the region of convergence is very important here to, make this statement accurate. Otherwise, we may have something that has no meaning. For example, if you go back to the basic point says this is true only if absolute value of x less than 1. Otherwise, if someone by mistake missed writing this, so it seems that this is always true, maybe someone will substitute 2, for example, in both sides. So he will get here 1 over 1 minus 2, that is minus 1. And on the other side, he will get what? 1 plus 2 plus 4 plus 8 plus etc. And this is not possible. You are adding positive numbers. So no way you can get what? Minus 1. Why this is wrong? Because we are substituting by a point which is outside the region of convergence. So for sure, this will give meaningless equation. Okay, fine. More about representation of functions by power series. This is very interesting subject. What is next? Now, what we did until now, we succeeded to rewrite rational functions, specific type of rational functions, as a power series. So let us add one more and see if we can get it here. Assume we are interested in finding the representation of 1 minus x all squared. This is not similar to 1 over 1 minus x. In the previous example, we have only what? Up to a first order here, 1 minus x. Okay, x squared, x cubed, no problem, but not all squared, not all cubed. Okay, so what should we do then? Another question here is, 1 over 1 minus x all squared is not of the form 1 over 1 minus x. Is it the derivative of some function, rational functions of order 1? Okay, let us see this. Is this one the derivative? This is the derivative of 1 over 1 minus x. Is it like this? Can we obtain it from the derivative of the basic function we have? This is the question. Can we get this function, this new function, by differentiating a simple function, let us say in other words, a function that we can find its representation? The answer in this case, yes. This is the derivative of that function. Okay, fine. From the previous identity, we have the representation of this. We have the representation of this to be n equal to 0 up to infinity of what? X to the power n, and we know that this is true if absolute value of x less than 1. So, the next question will be, can we differentiate a power series? Can we differentiate a power series? If we can do that, how to do it? And what is the new radius of convergence? That is one point we need to discuss. A second one, if we have something like logarithmic function, len of, for example, 1 minus x or 1 plus x. Okay, this is not a rational function, but you can figure out that this is actually the minus the integral of dx over 1 minus x if you are working again in absolute value of x less than 1. This is exactly equal to this. Okay, the question now. Since we have the representation of 1 over 1 minus x, can we get also the representation of this by the integral process here? So the second question, can we integrate a power series? Because at the end we can represent this one, I mean 1 over 1 minus x by a power series. Can we integrate a power series? Yes, we can integrate a power series and we can differentiate a power series. How to do this? This will be our next point. Okay, let us see now how to differentiate and integrate over power series. Assume we have a function that can be represented by a power series. You know, this is the form of a power series. Expanding some terms, we have c0 plus c1 x minus a plus the nth term here is cn x minus a to the power n plus this is up to infinity. Now, assuming also that this series is convergent with a radius of convergence is equal to r, then we have two interesting things here. How to differentiate over a power series? This theorem says, okay, if you can always differentiate term by term, if you are inside the interval of convergence, you can go inside and differentiate term by term as you are differentiating a polynomial. So the only thing, you just take the exponent down and decrease by 1. So that is n cn x minus a to the power n minus 1. Now, why the index is starting from 1, not from 0? Because you know, when you differentiate the right-hand side here, c0 will disappear. So terms will start from c1. c0, the derivative of c0 will be 0. The derivative of this would be c1. So the counting now will start from what? From 1. But if you need to integrate, again, you can go inside and integrate if you are working in the convergence. Okay, if we go inside and integrate term by term, this will be cn x minus a to the power n plus 1 divided by n plus 1. But be careful here. The index again is starting from 0. Why is that? Because once you integrate the right-hand side, c0 will not be destroyed will be there. C0 times x minus a. If you integrate, this will be 0 times x. So again, the counting in the integral will start again from 0. What is the benefit of this? Okay, of course, it gives a very nice result about differentiating and integration of a power series. This is one thing. And the second point, it will enable us to add more functions to our list. We can represent different now functions by using the integration and differentiation. But here is very interesting point also we need to address on. That is, if the original series has a radius of convergence is equal to r, after differentiation or integration, then also the new series obtained will have the same radius of convergence. It will not change the radius of convergence. Okay, fine. Let's go back to this example here. We said we cannot do it directly by the previous idea. But now, looking at this as it is the derivative of a well-known function, meaning I can look at this as the following: 1 minus x all squared. This is nothing but the derivative of the well-known function 1 over 1 minus x, meaning it is the derivative of a function whose power series representation is known. That's what I mean by a well-known function. 1 over 1 minus x, what is it equal to? D by dx, what is 1 over 1 minus x? I will replace it by its power series representation. That is n equal to 0 up to infinity of what? X to the power n. This is the geometric series. I know that this series is valid if absolute value of x is less than 1. This is convergent if absolute value of x is less than 1. By this discussion here, we can insert the differential operator inside and then differentiate term by term. So what will be the result then? I need to start now from n equal to 1 up to infinity, and that is n times x to the power n minus 1. Again, the radius of convergence is equal to 1, so this is valid if absolute value of x is less than 1. So you can see now we can get the answer of the power series or the representation of this function by power series directly by using the derivative operator. Okay, I have small remark here. We can get some beautiful results from representing a function by a power series. Look for this nice exercise, for example. Okay, if someone asks us what is the exact sum of, and he wrote here like n equal to 1 up to infinity, and we have something like n times, okay, let me write it this way. It is like n all over, that is 4 to the power n minus 1. What is the exact sum of this? It seems this is not one of the famous series we have. It's not a geometric series, for instance. It's not a geometric series because these are the two series we are done up to now where we can find the exact sum of them. It's not easy to find the exact sum of such a series unless we figure out that this is a series that can be obtained as a special case of the representation of this function. Look here. What I did actually, I substituted only x equal to 1 over 4. That's exactly what I did. X equal to 1 over 4. If we need to make it simple, okay, let us do it here like 1 over 2 only. Okay, so I'm substituting instead of 1 over 4, 1 over 2. What I am doing here, I choose a point inside the interval of convergence. I substituted here by x equal to 1/2. So that will give me 1/2 to the power n minus 1, or 1 over 2 to the power n minus 1, multiplied by n. But this representation says that this function is always equal to this inside this interval. So simply, what is the final answer then? The final answer, by that discussion, it says that you can substitute here x equal to 1/2. 1 minus 1/2 will be 1/2 squared to get 1/4. When you take the reciprocal, this will be exactly equal to, this is exactly equal to 4. Although this is not straightforward to be done by definition, but we can now get it as a special case of a power series. That is always interesting results we can get from the representations by substituting specific points we get some beautiful results, and we will see more about this in this talk. Okay, let's consider another function now. Let's add more functions to our list where we can find the representation. Let us discuss this function. Find the power series representation of f of x equal to ln of 1 minus x. This is the function I raised before. How to get the representation of ln of 1 minus x? So I need to ask myself, is it a rational function so that I can link it to the geometric series 1 over 1 minus x? The answer is no. Is it the derivative of a rational function that can be linked with 1 over 1 minus x? The answer is no. Next, is it the integral of a function that can be represented by a power series? Is it the integral of a rational function, in other words? The answer is yes. Okay, so I can see clearly that the logarithmic function here, which is ln of 1 minus x, is, I will say it is minus the integral of 1 over 1 minus x dx. Of course, if, again, absolute value of x less than 1, because otherwise we need absolute value, but inside that region, I'm sure that this quantity is positive, so I do need absolute value. So I will say, yes, the logarithmic function is presented by this. Fine. Can we represent this one by a power series? The answer is yes. So this is equal to minus the integral of, now I have a representation for that by power series, so I will substitute for it. It's n equal to 0 up to infinity, and that is x to the power n. I need to integrate this power series with respect to x, and according to this discussion we made here, that yes, you can always integrate a power series whenever you are working in the convergence region. Okay, fine. So this implies I have ln of 1 minus x is equal to, integrating now, switching the summation with the integral because we have the absolute convergence here. So what should we do? We have minus summation. This is n equal to, again, 0 to infinity because we are integrating, not differentiating. And this will give x to the n plus 1 over n plus 1, okay? Plus constant of integration for sure, which is equal to c. I suppose to write here the integral plus, of course, plus constant of integration, okay? So when once you integrate, you need a constant of integration because you are looking for the most antiderivative of the function. Fine. So I need to add a constant of integration. Always, I don't forget the constant here. And by that theorem, it says the radius of convergence, again, here is equal to 1. So I need this one to be absolute value of x less than 1. Okay, let us choose a specific point between minus 1 and 1. Say 0, for example. That's an easy point. If I substitute 0 on both sides, here I will have 0, and here I will have ln of 1, which is again 0, so this implies c equal to 0. So if we put x equal to 0, this implies the constant will be 0. So what does it mean? It means ln of 1 minus x is equal to summation. Okay, this is n equal to 0 up to infinity, and that is x to the power n plus 1 over n plus 1. Okay, we can also shift the index. I can start from 1, for example, 1 up to infinity. I'm increasing here by 1. I decrease inside by 1, so I will have x to the n over n. Again, this is true if absolute value of x less than 1. There is a minus sign here, right? There is a minus sign. There is a minus sign here. I don't forget the minus sign, which is outside the summation. Let us look for a very beautiful result from this. What can we say about this summation? N equal to 1 up to infinity. That is 1 over n times 2 to the power n. Okay, this is very interesting series now. If this n is missing, that is straightforward. This is geometric series. But since this is appearing here, is it possible to find the exact sum of this series? By the routine work we did before, it's not possible. But now, after discussing the representation of functions by power series, we can look at this as it is a special case of our result here. Look, what I did, I am substituting here by 1/2, so that I get this. 1 over n, 2 to the power n, that is, I am substituting for x by 1/2. Okay, if we substitute in the right-hand side by 1/2, it means we can substitute also here by 1/2. 1 minus 1/2 is equal to what? It's equal to 1/2. So what do we have? We have ln of 1/2 in the left-hand side. We have minus n equal to 1 up to infinity, 1 over n, 2 to the power n, which is the thing we are looking for. But what is ln of 1/2? Ln of 1/2, you can write it as minus ln of 2. Minus with the minus will be cancelled out, so the final answer is ln of 2. Fine, interesting. You see now, this beautiful result says we are adding actually infinite number of rational numbers. We are adding infinite number of rational numbers, and the final answer exactly is a rational number. A rational number, and you can see now this can be gained directly as a result of representing a given function by power series. Okay, let us see more about representation of function as a power series. Let us do it for a very famous function we have, very nice function called the tangent inverse. Tangent inverse of x. Okay, so the question always in this discussion says, find a power series representation of the given function. Find a power series representation of the given function. So let us say, for example, this is part f, which is a function given by tangent inverse of x. One of the famous functions we have in calculus. Tangent inverse of x. Is it a rational function? No. Is it the derivative of a rational function? No. Is it the integral of a rational function? Yes. So it seems we can find the power series then. So, okay, I will look for tangent inverse of x as it is the integral of 1 over 1 plus x squared dx. I know that this is the integral of this. The question is, can we represent this one by a power series? The answer is yes, we can do that, because I can rewrite it as 1 over 1 minus x squared, okay, dx. And clearly now I can find the summation or the power series representation of this function by the summation from n equal to 0 up to infinity, and that is what? That is minus x squared all to the power n. Okay, fine. I need to integrate this, all of it, with respect to x. I'm sure that this is true if absolute value of x again less than 1. That is absolute value of x squared less than 1. So simply what do we have? Let us simplify, then integrate. Let us simplify, then integrate the result here. Now, simplifying and integrating will lead us to the following. Look, I will write this one as minus 1 to the n, x to the power 2n first. So that is just summation. And I have here n equal to 0 up to infinity. And that is what? That is minus 1 to the power n, x to the power 2n. Okay? Minus 1 to the n, x to the power 2n. And I need to integrate all of this with respect to x. Okay, fine. The representation here makes sense if absolute value of x again less than 1. Fine. I need to switch the summation with the integration. I can do that if we are still inside the region. So it's okay. So I will write it like n equal to 0 up to infinity, and that is minus 1 to the n, x to the power 2n plus 1, integrating term by term. So this will give me the answer plus constant of integration. Again, by choosing a specific point, for example, let us say x equal to 0, I will have, okay, setting x equal to 0, if we put x equal to 0, this will lead us to the following here, c to 0. Because I have tangent inverse of 0, which is 0, everything here is 0, so c will be equal to 0. And in conclusion, this implies that tangent inverse of x can be represented by the following summation: n equal to 0 up to infinity minus 1 to the power what? N x to the power 2n plus 1 all divided by 2n plus 1. Fine. Let me say some words about this nice result we got here. This is a very interesting series. Tangent inverse of x can be represented by this. Although we know that this is true for absolute value of x less than 1. We are sure now this is convergence inside that region. Also, it can be proved that, it has been proven, actually it's not straightforward, but it has been proven that this series still valid if x equal to 1 or x equal to minus 1. So let me write this one as a remark here. Let me add it as a remark, although this remark, the proof of it is not straightforward, but this is well-known result we have for this specific function tangent inverse. I will say here, remark, this series is convergent if x equal to also plus or minus 1. If x equal to plus or minus 1, still this series is valid. What is the beauty of this? Okay, let me ask you a question. What is the sum of n equal to 0 up to infinity? What do you expect the sum of this will be? Minus 1 to the power n all over 2n plus 1. Okay, according to our previous discussion, that this is convergent series for sure because it is alternating whose bn terms, okay, decreasing and goes to 0 as n goes to infinity. So for sure this is convergent. But what is the exact sum of this? A beautiful result can be gained from the representation of tangent inverse and the remark I wrote here. Look, what is this? Exactly equal to what? What is it equal to? Look for the nice representation we have here. We said this is still valid if x equal to 1. So if I substitute here 1, I have minus 1 to the n over 2n plus 1. Substituting 1 in the left-hand side, the answer will be pi over 4. Amazing, amazing result here. Look, what we are saying here that if we just open the left-hand side, you have 1 at 0. This will be 1 minus 1/3 plus 1 over 5 minus 1 over 7 plus. This is equal to what? Okay, you are looking for rational numbers, alternating behavior, 1 minus plus minus plus minus added to each other, and at the end, the final answer is something related to pi. No, it's exactly equal to pi over 4, meaning if you are adding infinite number of rational numbers, it is not necessarily the final answer will be rational number. You can see now it is a rational number. It is a representation of pi actually. Pi over 4, if you multiply by 4 here, you will get a representation of pi by an infinite sum of rational numbers. Something very beautiful in my opinion. Okay, fine. What else we can gain from representations of functions by power series? You can see here we can gain so many special cases by substituting a point from the interval of convergence. We get some beautiful results like, for example, this one, like the previous one here, and etc. What else we can do by representing a function by a power series? Okay, we can also gain the following. Let us see this example. We can find some integrals that seems to be difficult. For example, I will say evaluate the integral of 1 over 1 plus x to the power 7 with respect to x. By elementary techniques we did in calculus 2, this seems to be not an easy exercise. Even if you use a computer program, most of the answers given will be a little bit complicated. An alternative way to do it is to find the answer as a power series. So I will say evaluate this as a power series. How to evaluate this one as a power series? we can use that nice theorem we wrote for integration and etc. So let us go back and see if we can represent this one by a power series. Okay, we know that 1 over 1 plus x to the power 7 is equal to 1 over 1 minus x to the power 7, isn't it? This is what we have, just rewriting it in that form. So, this can be written as summation of n equal to 0 up to infinity, that is minus x to the power 7 to the power n, or minus 1 to the power n, x to the power 7n. Fine. Meaning, I can represent the function here inside by a power series. Okay, this is true, again, if absolute value of x less than 1. By using the previous result we have for integration and differentiation over power series, it seems that the integral of this function can be obtained by integrating the power series here. So, I can rewrite this as this implies the integral of 1 over 1 plus x to the power 7 dx is the integral of this with respect to x, so that will give n equal to 0 up to infinity minus 1 to the power n x to the power 7n plus 1 all over 7n plus 1 plus for sure constant of integration. So this is another penalty. Of course, this is true for absolute value of x less than 1. So this is another application for representing a function by a power series. You may end up with integrals that are difficult to be calculated. An alternative way to evaluate is to represent that function by a power series, then integrate, and then you can estimate your integral. You can estimate your integral up to whatever order you like, because at the end of the day, you have an estimation theorem we did before for alternating series, so you can choose the number of points needed so that you have a certain accuracy. So this is alternative way to, if we cannot integrate something, then we can represent it as a power series. Then, as a consequence of this, we can always approximate integrals by using power series. That is the first step in representing a power series. You can observe now what we did. We succeeded to represent only special type of functions. Rational functions, functions that can be obtained from rational functions by either integration or differentiation. What other functions we can do? That will be done in the next talk. Okay.